Today. We have lots to do. I made a list for myself on the board here. So last class I introduced you to skip lists, and I showed you that they could be used to implement sorted sets, and they could be used to implement lists in which all of the operations took logarithmic time, so order log n time. Just very briefly, remember how a skip list worked. In the case of a sorted set, you have one list called L0 that contains everything in your set in sorted order. There's also, at the head of this list, there's a magic node called a sentinel. And from L0, you make a list L1 by taking each node in L0 except the sentinel and tossing a coin. If the coin comes up heads, that node appears in L1. If it comes up tails, it doesn't come up to L1. So for example, you might get a heads, two tails, heads, heads, tails, heads. And then you repeat. From L1, you make L2. So here we have A, D, G, and E. From L1, you make L2 by tossing coins again. Maybe you get A again, and E. And then from L2, you make L3. Maybe you only get E in that case. And your skip list is this tower of these little towers of nodes. Each level of the tower is linked in a singly linked list. Every node has a node below it. Usually these are actually stored in a single array, but however you want to think of it, we can get from this node in L2 to the corresponding node in L1 to the corresponding node in L0. Usually that's implemented by just storing all those things in an array and then links across the levels. Okay? So that's the object of our study. And it's a randomized structure because it uses coin tosses to determine what goes up in these levels, or in practice it uses random bits or pseudo-random bits. And so if we want to analyze this thing, we have to use some tools from probability theory. So one of the things that I tossed around was this idea of the expected size or expected length or expected time. So what does that mean a little bit more precisely? I don't want to go into a course on probability theory. If you're taking, I believe it's something like 2804, is that right? It's discrete math 2. You'll get some discrete probability. You haven't analyzed skip lists there yet, have you? No, you may or may not. Have you talked at all about probability in that course yet? Just started. Okay. So here's the thing you want to know. A random variable is just something that can take on different values. With different probabilities. If you pick a random person, well, that's a thing, that's a random thing, and you say, what is the height of that person in centimeters? Well, that value, that's a number, that's a random variable now. So if you take a random person off the planet, say, what is the height of that person in centimeters? Then that's a real number for any particular person, but because it can take on different values, we call it this random variable. And there's this notion of expectation or expected value of a random variable, which is just its average. So if x is a random variable, we might write something like this. The expected value of x is the sum over all possible values that x might take of that value times the probability that we get that value. Okay? So, if we were trying to measure the height of, the average height of a person on the planet Earth, then we say we add up over all people of, let's say, height 100 centimeters. We take 100 times the probability that the person we get has 100 centimeters. And then 101 times the probability that the person we get is 101 centimeters, and so on. Okay? And this gives you a meaningful definition of average or expected value. This is kind of awkward to work with, so I'll show you a couple of tricks. And even better, these sums are a bit annoying. We'll be working with really simple random variables. So an indicator random variable is a random variable that takes on the values 0 or 1. So it's a really simple one. So if we say that, let's say, I is an indicator random variable, then we can apply this formula, which is the sum over all the possible values that I can take on to get the expected value of I. So I can either be 0 or it can be 1. So this sum has two terms. One of them is 0 times the probability that I equals 0. And the other one is 1 times the probability that I equals 1. Okay. That's just this definition here in the very simple case of random variables, which only take on two different values. Can we simplify this a little bit more? There's two terms in this thing. Can we bring it down to 1? Yeah. So this is never going to contribute anything because whatever this probability is, we're multiplying it by 0 anyway. So this is 0. So really, these indicator random variables are really nice because if you want to know their expected value, well, all you care about is the probability that they're equal to 1. Okay? This 1 multiplying by 1 doesn't change anything either. So that's the expected value of an indicator random variable. Okay? Good. And now the last sort of tool from probability that we need is what's called linearity of expectation. It's one of the nicest things about expected values that allows us to do prove all kinds of incredible results. And it just says that if we have two random variables, A and B, and we want to know the expected value of A plus the expected value of B, that's just equal to, the expected value of A plus B is just equal to the expected value of A plus the expected value of B. Okay? So I pick two random people. I want to know what is the sum of their heights. Well, it's enough for me to know what is the sum of the height of one random person, what is the height of one random person, and what is the expected height of the other random person. Okay? And more generally, this is just a special, this is just a sum with two terms. More generally, the picture looks like this. The expected value of a sum of random variables is just the sum of the expected values of those random variables. Okay. This is just the case when the sum has two terms, but in general it works this way. All right. So let's see, let's try and use these three things to prove something. All right. So here's an experiment. Toss a coin until it comes up heads. So I will say that x is a random variable is equal to the number of coin tosses we make. Okay? So it's an easy experiment. I pick up a coin and I toss it once. If it comes up heads, I stop. If it comes up tails, I toss it again. If it comes up heads that time, I stop. If it comes up tails again, I toss it again. And so on. And I stop the first time it comes up heads. Okay? So the number of coin tosses I make is a random variable. Things we know about it, well, it's at least one, because I have to make at least one coin toss. But it could be, you can't say that it's less than 10. You can't say that it's less than 50. You can't say that it's less than 100. It could be that I tossed the coin 99 times, and it came up tails all 99 times. So it's really this random variable. And then we can ask about its expected value. Okay. Now, I can apply this formula here and say I sum up over all the values. So we can write down that formula, but I won't do it. We'll see a different way to do it shortly. So to get that, what I have to do is sum up over all the possible values that this variable could take on. So what are the possible values for this number of coin tosses? So this sum starts where? 0? 1. So there's no, we have to toss at least one coin. And it stops where? It doesn't. It has to be, it's an infinite sum. For every integer, positive integer n, there's some probability that that's exactly how many coin tosses we make. We toss n minus 1 heads, and then we get n minus 1 tails, and then we get the first heads. Okay? So we would be summing I times the probability that x equals I. Okay. Well, this I kind of know, or I can figure out easily. What is the probability that I make exactly I coin tosses? What's the probability that I make exactly one coin toss? Yep. Yeah. So, but it's the right answer. It's a half. So, with probability of half, we toss the coin. The coin comes up heads on the first toss, and we stop. So that means we made exactly one coin toss. And the probability that we toss the coin twice is exactly a quarter, because that happens when the first coin toss comes up with probability, comes up tails, and the second one comes up heads. So in general, this is I times 1 over 2 to the I. And if you're good at sums, then you can figure out what this is. I want to show you a slightly different way of doing that, using indicator variables. So instead, I will define an indicator variable. Let's call it I sub j. So it's supposed to take on two different values, either 1 or 0. It's an indicator variable. And it takes on the value 1 if we toss the jth, or let's say if we make the jth coin toss. And it comes up 0 if we don't. Make the jth coin toss. Why would we not make the jth coin toss? Well, we would not make the jth coin toss if one of the first j minus 1 coin tosses came up heads. Then we don't have to make the jth one, right? Okay. So the thing I'm trying to count is the number of coin tosses we make. I define this variable, these sequence of variables, I sub j. J goes from 1, 2, 3 up to infinity, that tell us whether or not we make this coin tosses. Okay? So actually, I can redefine my variable x and just say that this is just I1 plus I2 plus I3 plus I4 and so on. Right? This sequence of i's here, this will always be 1. This one will be 1 if we had to make a second coin toss. This one will be 1 if we had to make a third coin toss. This one will be 1 if we had to make a fourth coin toss. Eventually, coin comes up heads. That last one has this indicator variable equal to 1. But after that, we don't make any more coin tosses. So all of the remaining ones are 0. It's just another way of writing this thing down. And now, we were interested in, so let me write this a little bit more precisely as a sum. So this is just the sum as j equals 1 to infinity of I sub j. And we were interested in the expected value of x. That's what we're trying to study. So that means we're interested in the expected value on the right-hand side as well. And we like that these indicator variables are so easy to get their expected values. We want to make use of that. And so we use linearity of expectation to do that. Okay. That's this piece of the puzzle over here. The expected value of a sum is the sum of the expected values. Good. Now, we would like to know what these things are. So what is this expected value of I sub j? Well, let's see. What do we need to know if we want to know the expected value of I sub j? I sub j is an indicator random variable. There's only one piece of information we need to know its expected value. It's written on the board. So I sub j is either 0 or 1, and its expected value is equal to what? It's written over here. We just need to know the probability that it's equal to 1. Okay? So, I sub 1 is equal to 1 if we toss the coin the first time. So, what's the probability that I sub 1 is equal to 1? 1. We always toss that coin. Okay? So the expected value of I sub 1 is equal to 1. What's the expected value of I sub 2? So when do we have to toss the second coin? Yep. Well, yeah. So we'll have to make a second toss, which is what happens, what it means to have I sub 2 equal to 1, if and only if the first toss came up tails. And the first toss comes up tails with probability 1/2. So I sub 2 is 1/2. What's the expected value of I sub 3? This is where my daughter would say 1/3. Yep. 1/4. So if we need to toss a coin a third time, that's because the first two coin tosses came up tails. And that happens with probability 1/4. And then if we need to toss the coin a fourth time, that's because the first three came up tails. That happens with probability 1/8. And in general, the expected value of I sub j is equal to 1/2 to the j minus 1. Okay? And now it's actually a little bit easier. Since we've already started writing down all of the terms in this sum, we can write them down here. So what does that add up to? 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 32nd. That adds up to 2. Right. This is the famous Zeno's paradox that, I don't know, posed by a Greek philosopher who said, how is it that we can run marathons? How is it that anybody can run a marathon? Because, you know, a marathon is 2 units of distance for some unit of distance. And before we can finish a marathon, well, we have to run halfway. So we have to cover 1 unit. And then, and then we still have to do the same thing again. Before we can finish that, we have to cover a half unit. And then we're left with a half unit. Before we can finish that, we have to cover a 1/4 unit, and then an 1/8 unit. Of course, there's no real paradox here. But this argument does show that no matter how many times you do this, you never quite make it up to 2 here. In fact, it's only in the limit when you take the sum all the way to infinity that you get up to 2. Our sum does go to infinity, so we actually get an equality here. Okay? So, no big surprise, I hope, for most of you. If I toss a coin until it comes up heads, then the average number of times I have to toss that coin is 2. That actually tells us something else. We have this sum here that you may or may not have known how to do, but now we know the answer to this because we found a totally different explanation for it. It's equal to 2. And if you like calculus, taking derivatives, you can figure out the relationship between these two things. Okay. Questions so far? So it turns out I didn't do this coin toss thing for nothing. It turns out to be important for us. So that's good. And we'll have to analyze a few things like this. All right, so expected value, indicator variables, linearity of expectation. We studied coin tosses. So something that we argued roughly about last class in a sort of imprecise way, but now which we can make completely precise. We can say, let's look at the sizes of these lists. Let n sub I equal the length of list Li, not including the sentinel, and so now we say, well, first question is, what is the expected value of n sub I? For L0, there's no question here. By definition, the number of elements in it is n, so there's nothing random about that. But for L1, L2, L3, and so on, these things are random variables. We don't know exactly how many elements are here. It depends how the coin tosses came up. So makes sense to ask about the expected value. Okay. Well, here's a way to handle that. Let's say ij is a random variable which takes on values 1 or 0 and takes on the value 1 if j appears in L sub I, and it takes on the value 0 otherwise. Okay. So the values of j here are the values, the possible values of j are the values in these nodes in L0. Okay. So what's the expected value of ij? Okay. So I have something j here in the bottom list. So how does a node make it from L0 up to L sub I? Yep. It has to, so a node gets promoted out of L0 if its coin toss comes up heads. So close. So from L0 into L1, we had to make one coin toss that comes up heads. From L1 into L2, we had to make a second one. And in general, to make it all the way up to L sub I, we had to toss a coin I times, and it came up heads every single time. Well, what's the probability that we toss a coin I times and it comes up heads every single time? Yep. 1 over 2 to the I. So it doesn't depend at all on j. I mean, it's the same probability for any element in this bottom list here. It really only depends on which list you're asking if it made it up to. Okay. All right. Now we're good to go. So what is n sub I? The number of elements in that list Li. Well, I can get that by summing over all the j's in L0 of I sub j, right? Just for each element in list 0, I count it as a 1 if it appears in L sub I, and I count it as a 0 if it doesn't. And now I take expected values. I use linearity of expectation. I look at the board and see that I know what this quantity is. How many elements are in L0? There's n of them. So this is just n over 2 to the I. Okay. So now we know what is the expected number of elements in the list L sub I. That's useful. What we're probably more concerned about is the size of the whole data structure. And for that, something we're interested in is, how many things are in the list L0, how many things are in the list L1, how many things are in the list L2, how many things are in the list L3, and so on. And in general, we have no upper bound on the height of this thing, so there's somehow an infinite sum here. This infinite sum we're talking about is the sum I equals 0 to infinity of n sub I. We would like to know the expected value of that thing, because that tells us how big the entire data structure is, not counting the sentinel. So, what should we do next? So, we've done this twice already. I have the expected value of a sum. So I have the expected value of this complicated thing. I want to break it into simpler pieces that I know how to study. So which trick do you use for that? Yeah, linearity of expectation. That's just this trick of saying, let's not worry about the complicated thing. We don't need to, we just need to understand its parts. And we have a formula for the parts. It's right here. Expected value of n sub I is n over 2 to the I. Well, this is an infinite sum with an n in every term, so we factor that out. What's this sum here? It's written on the board. I'm pointing at it. This thing here, this is this 1 plus a half plus a quarter plus an eighth. So that's 2. So this whole thing is 2 times n. The total expected size of all the lists is 2 times n. Not bad. So it's not outrageous. All right. That's all been playing the same trick repeatedly. Now it's time to get to something that requires a little more cleverness. So ultimately, the thing we're trying to get to, well, it's nice to know the size, but there's other things we're trying to get to. One of the things we're trying to get to is understanding the expected length of a search path. That is this path that starts at a node in the bottom list, if you like, and it goes up if it can. Otherwise, it goes left. It does this greedily, trying to go up whenever possible. If not, it goes left until it reaches the top occurrence of the sentinel up here. Alternatively, you start at the sentinel and you go right as long as you don't overshoot the node in the bottom list or reach it. If going right would cause that to happen, then you go down instead. That gives you the same path. That's the thing we're trying to study, and we'd like to get to that. The search path has a couple of components to it. Well, two. Sometimes the search path goes down, and sometimes it goes to the right. So the first thing we'll study is how many times do we expect this search path to take a step down? Okay. Well, we kind of know that in advance. It doesn't matter which node you start at, the search path has to start at the top left here, the top level, and work its way down to the bottom level, and each step down takes it one step closer. So really, to understand how many steps down the search path takes, it doesn't matter which node we're looking at, it's just asking how high this list is. Okay? So what's the height of the sentinel, which is just the height of the highest node, the longest surviving node. Okay? All right. So we would like to know the height of this skip list, or if you like, we would like to know the number of lists it contains. That's the same as the height. Okay? All right. Or, the maximum value of I for which L sub I is non-empty. These are all plus or minus 1. They're all the same thing. Okay? So, so let's say we want to know the expected number of, let's say, values I such that L sub I is non-empty. Let's call that thing H for height. And we want to know the expected value of H. That's the thing we want to study. All right. Well, we want to break this down into simple, manageable pieces that we have some idea how to study. So let's look at let's define some indicator variables, I sub I is equal to 1 if L sub I is non-empty, and it's equal to 0 if L sub I is empty. Okay. So in this example here, we have I sub 0 equals 1, I sub 1 equals 1, I sub 2 equals 1, I sub 3 equals 1, I sub 4 equals 0, I sub 5 equals 0, and it's a big stack of zeros after that. Okay. Well, so let's go back to our H here. H is supposed to be the number of non-empty lists. So the number of values I such that L sub I is non-empty. And this thing happens to be 1 if L sub I is non-empty and 0 otherwise. So H is just the sum of these things, right? How many non-empty lists are there here? There's 1 plus 1 plus 1 plus 1 plus 0, 0, 0, 0, 0. Okay. Would anyone like to pause here? Yep. Yeah, no, L3, I stopped here because implicitly, this thing came up tails. I tossed again for E, and it came up tails. And no, it stops when the size of the list is 0. Okay. All right. So again, we're interested in the expected value of this height. And we've boiled it down to the expected value of some complicated sum. What should we do next? Yep. We split it using linearity of expectation into hopefully easy parts. I mean, how hard can these things be to study, right? They only take on 2 values, 0. I don't know that quantity. I can't tell you exactly what the probability is that L sub I is non-empty. I don't know. I can tell you maybe for I equals 1, but already for I equals 2, it gets a little bit iffy. So we need something. We need to do a trick here, okay? So let's look at some things we can say about I sub I. Here's something I'll tell you for free. This variable, whose value is 0 or 1, is less than or equal to 1. Do you believe that? That's always true, right? If it's either 0 or 1, that means it's always less than or equal to 1. So that means its expected value is also less than or equal to 1. That's good to know. Okay. That's still not good enough, because if I go back to this sum and just say, oh, look, that says that this is less than or equal to the sum I equals 0 to infinity of 1, well, that's infinity. So yes, the expected height is less than or equal to infinity. We didn't even get strict inequality, so there's an issue there. So that doesn't help us yet. We need another inequality here that's useful, more useful than this. Can you tell me anything else about I sub I? Is there another thing that you could say it's less than or equal to? Yeah. Yeah. It's less than or equal to 2n. Why do you bring n into it? Yeah, so it's less than or equal to somehow the size of the whole thing, but I mean 2n seems really big when this is less than or equal to 1, but there are some n's that this may be useful for. Yeah?
Is I also less than or equal to 1 as well?
Well, the I, knowing this, you mean this little I here? Yeah, this doesn't help us. Yeah, the big I is less than or equal to 1. That's what we have up here. But it's also less than or equal to n sub I. Let's think about that for a second. If the list, so we have to verify that this is true. So if the list L sub I is empty, that means that I sub I is equal to 0. What's n sub I then? 0. If the list is empty, it has 0 elements in it. So it's true in this case. And if the list is not empty, that means it has at least one element. So n sub I is bigger than or equal to I sub I in that case as well. Agreed? So, I mean, I sub I, another way of saying this is it's equal to 1 if n sub I is bigger than or equal to 1, and it's equal to 0 if n sub I equals 0. And notice that in either case, n sub I is bigger than or equal to I sub I. This doesn't seem really useful, since we already know I sub I is smaller than or equal to 1. It doesn't feel useful at the beginning because this seems like some huge number, n, right? We have millions of elements in our list. Then, I sub I is less than or equal to millions. But actually, that's not quite true. If this is true, if I sub I is less than or equal to n sub I, it's also true that its expected value is less than or equal to the expected value of n sub I. And the expected values of n sub I, actually, sometimes they get quite small, smaller than 1. All right? We know what they are. Expected value of n sub I is n over 2 to the I. Okay. So the expected value of I sub I is less than or equal to n over 2 to the I. And sometimes that's small, much smaller than 1. So now, all we have to do is take this equation and split it into parts where in some parts we apply this inequality when it's good, and in other parts we apply this inequality. So here we go. This thing, we can take this sum, I equals 0 up to, let's say, the ceiling of log n. We split it into two parts. One just goes up to the ceiling of log n. The other one starts at the ceiling of log n plus 1 and continues to infinity of the expected value of I sub I. Okay? And we have two inequalities for these things. So these ones, can't say too much about them except that they're all less than or equal to 1. So let's get that out of the way right away. One. That leaves these other ones. And these ones here, well, we might as well apply the second part. They're all less than or equal to n over 2 to the I. Okay. So all this is saying is that, I mean, if we want to interpret this, we're saying that if you look at the first log n lists, so starting from here, they're probably not empty. So we're willing to just give up on those and say, yeah, I'll count those first log n lists as if they're surely not empty. But after that, once I get beyond the log nth list, there's a reasonable chance that these things are empty. So rather than taking their, using this variable directly, I'll just take their expected sizes, which we argued here, you know, the expected size of this list is definitely bigger than or equal to this indicator variable. All right. Okay. So we have this sum here, and let's look at it closely. This is basically a sum that starts at n over 2 to the log n plus 1. So what's 2 to the log n? N. So this is n over n times 2. That's what you leave the plus 1 behind here. So this is n over 2n. So this sum starts at a half. In fact, when you take the ceiling over the log n, which is what we have here, then all that means is you get an inequality here. Okay. So the first term here, when we take I as log n plus 1, the first term here is a half. What's the second term? Well, that's n over 2 to the log n plus 2. And so that leaves n over n 2 to the 2, which is a quarter. And the third term is with a plus 3 here, n over 2 to the 3. So that gives us an eighth. So actually, this part here is just 1/2 plus 1/4 plus 1/8 plus 1/16, or it's less than or equal to, plus 1/32, which is less than or equal to what? 1, right? This is the same argument as before, except now instead of starting with a step of size 1, we start only with a step of size 1/2. We'll never quite reach 1. So this, let's write this down again. The sum I equals 0, ceiling of log n of 1 plus this whole second part here we said is less than or equal to 1. This first part is just log n things. this is log n times 1, right? So, or log n plus 1. So this is ceiling of log n plus 1 plus the 1 from over here. And if you want just to tidy things up, that's less than or equal to log n plus 3. Because the ceiling of something is less than that thing plus 1. Okay. All right. So all of that to say that the expected height is less than or equal to log n plus 3. That's not easy. I mean, once one knows it, you can present it in a natural way that makes it evolve, but it's not a trivial thing to prove from scratch the first time. Okay. So, we know something about this search path. We know how many steps down it takes in expectation. All we have to figure out now is how many steps it takes to the right. And that's where we really have to use our imagination a bit. And look at this backwards view of this thing. So remember, the backwards view of the search path is you start at the node, some node in the bottom level. If you can go up, you go up. And if you can't go up, you go to the left. Okay. And we're interested in, and from that view, we're interested in these steps to the left here. Yep. Because there was a ceiling on the log n. And so we just used that. Okay, so we want to know this number of steps to the left. So let's say L sub I is equal to the number of steps the search path takes. Let's say number of horizontal as opposed to downward steps. The search path takes at level, or let's say in, oh, that's bad notation. Let's call that R sub I. Okay. So for this search path, we have R sub 3 is equal to 0, doesn't go to the right at all. R sub 2 is equal to 1, takes one step to the right. R sub 1 is equal to 1, and R sub 0 is equal to 0. It goes straight down. Okay. All right. So let's use our imaginations for a second. We imagine that we are trying to follow, we wake up here at this node in the bottom list, and we try and find our way, crawl our way out to the top left sentinel. And I don't know, imagine we have a very poor memory. So each step up here represents, a big night of partying so hard that when we get to the other end of the night, we don't remember anything that happened. Okay? So we've been doing this for a while. We started at the bottom. We took some steps to the right, to the left. The last thing we did was we took a step up. This step is up into list L sub I. We wake up from our night of partying and look around and say, okay, what happens next? We want to figure out now how we can get to the next party and up to the list L sub I minus 1. We're trying to get up to here. Now, we haven't done anything that depends on L sub I yet. This is the first time we reached L sub I. So we don't know anything about it yet. So one of two things can happen. Either this happens to be party night and we get to go straight up, or it's not party night and we have to go to the left here. Okay? So when does it happen if we get to go straight up? What has to have happened? Yep. Yeah. The coin that we tossed at this node in this list must have come up heads. If that happens, we get to go straight up. If not, if the coin comes up tails, then we have to go to the left. Okay. And if that, then we check again, do we get to go straight up? Well, that depends on whether or not the coin toss we made here came up heads or tails. And if that came up tails, then we'd have to go to the left again. Okay? So asking this value of R sub I that we're asking about here is basically like waking up, tossing a coin until it comes up heads. And then you ask, how many times did I have to toss that coin before it came up heads? So not counting that last one that came up heads. Right? If it comes up heads the first time, you don't spend any time going to the left. If it comes up heads the second time, well, you would have taken one step to the left, and so on. Okay? So R sub I, that is almost the same thing, and I'll put an inequality here and say that's just like number of coin tosses before getting heads the first time. And explicitly here, not counting the head, the one that came up heads. Well, so taking expected values, how often do we have to toss a coin before it comes up, before we expect it to come up heads? It's the first thing we did this class, the first example. 2. Is that exactly the same thing we're studying here? Almost, except there we counted the last coin toss that came up heads. Here we don't count it because that represents a step up, right? This would be a coin toss that comes up tails. Coin toss comes up tails. If it's heads, that's a step up. And R sub I is supposed to represent horizontal steps. But that is just equal to 1. It's not, we don't count the last coin toss. So on any experiment we do, we just subtract 1 from the other thing. So we get 1. Okay? All right, so the expected number of horizontal steps the search path takes in L sub I is less than or equal to 1. Okay. All right. So let's see if we have what we need. We're almost there, but not quite yet. So the length of the search path that's equal to number of vertical steps plus number of horizontal steps. Okay. Well, the number of vertical steps, we have a name for that. That's h, the height of this list. The number of horizontal steps, we have names for those. Those are called r sub i's. Okay? So this is where we've gotten to so far. The length of the search path is number of vertical steps plus horizontal steps. Vertical steps is called h. Horizontal steps in list I is called ri, so we sum that over all the values of I. And if we take expectations and we use linearity of expectation right away now, this is what we get. This quantity we know is less than or equal to log n plus 3. And we're left with this guy, which we can say is well, what do we know about the expected value of Ri? It is less than or equal to 1. Is that good enough? Nope, because if I put a 1 here, I get a sum of infinitely many 1s. We're not quite done. But we have seen how to handle this kind of problem before. We just need something else we can say about these RIs. So in this list here, L3, how many steps to the right can I take? At most, how many? Yeah. In this picture, exactly in this picture, how many steps? Yeah, no, not even the search path. Just if I try and walk through this list, how many steps do I take? 1. And then it's over. And what if I try and walk through this list? I can take 1, 2 steps. And then I can't continue anymore. And this one I can take 1, 2, 3, 4 steps. So something else I can say about the number of horizontal steps is that it is at most the number of elements in the list, right? So we proved that the expected number of horizontal steps is less than or equal to 1. But something else that's trivial is it's less than or equal to the number of elements in that list. Well, this is something we've used before. The number of elements in that list is less than or equal to n over 2 to the I. So we're left trying to deal with this thing, and we have 2 inequalities for the expected value of Ri. One says it's less than or equal to 1. The other one says it's less than or equal to n over 2 to the I. So we split it again at log n. For the first part, we use the inequality Ri, expected value of Ri is less than or equal to 1. For the second part, we use n over 2 to the I. And unless I got this wrong, this thing here is exactly what we have on the board over there, which we figured was at most log n plus 3. This is the ceiling of log n plus 1. This is at most 1. And so we finish with less than or equal to 2 log n plus 6. So we take about as many steps to the right as we take downwards. Seems like the right trade-off. Okay. So I can erase this. Write down the main theorem. Expected length of the search path for x is at most 2 log n plus 6. Okay? So that means, for example, if you have a skip list with 1,000,000 elements in it, you expect to have to look through about 46 of them before you find the value you're looking for. Log of 1,000,000 is about 20, so this is 40. That makes 46. Okay. So, any questions? So we didn't do too much. I mean, this is strange and new to many of you, but we didn't really use anything advanced or difficult here. The most powerful tool we had was linearity of expectation, and basically a clever way of breaking down things into these really simple indicator variables. Okay. So that's a good place to stop and digest things.